Great. So welcome to the second class. So today's class, we will cover chapters 3 and 4 of the Branges book. And so just as a quick reminder of the last class, so let me write it here. So what we did was, in the last class, we did the following. So we had a function, let's say, in the upper half plane, C+, so you have some function f here. And I want conditions on f so that, is there it? Oh, group study, okay. I want conditions on f so that I can guarantee that f of z is less or equal than 1 for all z. So I keep saying z and z for the variable for this guy here. It's just because Canadian is spent some time in Canada, and they say z instead of z. I think in US is z, or the opposite. I don't know. Anyway, so I'll keep interchanging. Okay, so that's what we wanted. We want some conditions, and we figured out that yeah, that can hold. So yeah, we can have this if well, on the real line, f is less than or equal to 1, plus some decay condition. And the decay condition was something like you take an average of the log of the function along a semicircle, and if send the semicircle to infinity, if that thing is 0, then we can guarantee that the function is less or equal than 1. That was the fragment Lindelof maximum principle. And then we used Poisson's representation to construct a function on the upper half plane f such that was always greater or equal than 1, assuming that I gave you any, let's say, initial data on the real axis. Let's say the real part of f of x equals that, and h is given. And also h is greater or equal than 1. Okay, so that was the second result, which I think is more or less here. Oh no, there was moduli of x, not real part. Yeah, so it was like this. Okay, so that was the second thing we did. And for that, we use, well, kind of ad hoc, but without much of explanation, but we use this representation, which is called Poisson representation. And in this class, we will characterize certain functions, which are functions on the upper half plane, which have no negative real part, as being given by the Poisson representation of, or Poisson extension, let's say, of some non-negative measure. Okay, so that would be the content of this class. So first we start with the converse, let's say. I will give you a measure, and then I want to extend that measure to an analytic function in the upper half plane so that it has no negative real part. So that would be theorem 3 in the Branges book. So let mu of x be a non-decreasing function of real x. And then we assume a certain decay condition, which we will see several times in this class. So we assume that it integrates when we divide by something like t squared. Then you define a certain function, let's say f of z equals, which using the same formula we did in the last, for theorem 2. The Branges likes to write this formula a bit different, but if you just work out through his formula, you see that's identical to that. So then this function is analytic in the upper half plane and has no negative real part. And furthermore, if, and I will explain this statement in a moment, if A and B are points of continuity, of this function, of this non-decreasing function mu, then mu b minus mu a equals the limit when y decreases to 0 of the integral from a to b, the real part of f iy dx. Okay, so in a certain sense, what we're saying here is that real part of f is equal to, let's say, dx is equal to the measure d mu x. That's basically what we're saying here. Okay, so this is the theorem. So a couple of words before we start the proof. So let me just recall here some stuff. So first of all, what is this thing here? What is the mu of t? And what I'm using here is what's called Riemann-Stieltjes integral. There is a Lebesgue-Stieltjes integral as well, but we won't need that. So what is that? For those who don't know, whenever I give you some function from an interval AB to the real line, which is non-decreasing, I can use that as a way of measuring intervals. So the length of an interval from A to B is going to be mu B minus mu A. So you put like a new length. So if you divide, so if you differentiate that length, you get a new measure. So basically, if G is, let's say, continuous, then you can define and you can actually show that this definition makes sense, which is going to be the limit when the length of the partition goes to 0. So it's basically just a Riemann integral, but using this measure as a length. So P is a partition here. So let's say x0 is A, is less than x1, is less than xn, which is B. And Ci is just any point in the interval xi minus 1, xi. Okay. That's the Riemann-Stieltjes integral, and you can show that this makes sense whenever g is a continuous function and mu is non-decreasing. This limit exists and therefore defines, this way this integral is well defined, okay? Oh, and the length of the partition, I should say, is just the minimum of xi minus 1. Okay. So just like Riemann's integral, but using this measure mu. So for example, you could take a measure, you could take a function which is just like a step function like this. So it goes from the interval a to b, and at some point p in the middle, it jumps from 0 to 1, let's say. Okay, suppose that's your function mu. So what that definition would give us, well, then the integral from a to b of g of x, the mu of x, would just be g of p. So basically what you're saying is that the mu of x is just the delta of a point p. Okay, that's what's going to happen. So you can write delta functions, and you can write all sorts of measures. So for instance, if you start with a measure on the line, then so this is a side comment. If you start with a measure, let's say the sigma, then you can define just mu of x as, let's say, integral from a to x of this measure, and then the mu of x will be the sigma of x. Okay, that's another way. But the Branges likes to use the point of view of starting with a non-decreasing function, and then you obtain a measure, not from the opposite side. From a measure, you have this non-decreasing function. Another thing is that, well, if it follows also from the definition that if mu is, like, say, C1, or even more, just absolutely continuous, if you don't know what that is, then you just think it's as C1, then the mu of x would just be mu prime of x dx, okay? Also follows from the definition. What else? Yeah, and basically that's it. Yeah, if you have points, yeah, I don't want to take, yeah, well, let's just leave it as it is. Any questions so far here? Okay, so let me just erase this part here. Let me, and let me just say, what else? This is one, and the other will be, let's just say this is mu C1. Okay, so basically that's what we need. Before we start the proof, let me see if we don't need something else. Oh, and in the statement also we had a thing called, well, if A and B are points of continuity of the measure, this is because, maybe I should explain this as well. This is because, well, when you do something like this, you have to specify what you're doing here, because, well, what do you mean by integrating from A to B? Because, for instance, at the point A, the measure could have a delta there. So do you mean that you're taking a limit from points in this integral? Do you mean this? let's see. If we do mean this, then we should say something like a plus here. I mean, coming from the right. Maybe you actually mean this, then you should put the B minus here. Okay, so these things are important. So it means that when I'm integrating something, I can't, if it's not continuous, if it's not absolutely continuous, then I can't, these things have to be specified if you are computing a measure in a closed interval or in an interval it's open on the left, on the right, etc. So I will use these markers, but I would use these markers to specify that, maybe in some other chapters, not in this class. However, if A and B are points of continuity, then all of these definitions are equal. So I should say if A and B are points of continuity, then all those definitions that I mentioned, plus or minus of B, plus or minus the mu of X, they are all the same because these are points of continuity, and it's just mu of B minus mu of A, okay? So in this sense, now this final result here now makes more sense because, well, I'm integrating f from A to B, and I'm taking that to the real line. So basically, I have like a certain interval here. This is A and this is B, and I'm taking this line down. So that should converge to the integral of mu from A to B. But if those are not points of continuity, I won't know what's going on at the point A or B because that will be a delta there somewhere. But if they are, then I can guarantee that this is just that, okay? Because, well, being points of continuity, that will be exactly equal to this, okay? Because these are points of continuity. So the integral here is converging to the integral of mu in the integral. So that's what the statement is saying. Any questions here? Okay, so we can move on to the proof. So first of all, let's look at the definition. Well, it's clear, well, from the same comments I made in the theorem 2 in the last class, this function converges, well, this integral converges absolutely as long as z is a point in the upper half plane. And this will define a analytic function easily. And then if you take the real part, we already did this computation. If you take the real part of f of z, then you just get the Poisson kernel. Okay, and that's clearly, this is just an easy computation, and this is clearly greater or equal than 0. Okay, so that part of the statement is good. The only difficult part is to prove the limiting argument, is to show that that when I take this limit, I get mu of B minus mu of A. Okay, A and B being points of continuity. That's just the crux, let's say, of the proof here. And for that, what we will do is we'll have to, well, basically we have to integrate from A to B this formula here. So we have to integrate from A to B this formula here, and then so you have to compute the primitive of this function here as a function of the function of x, and that primitive will be an arctangent. So we need some properties of the arctangent function. So, okay, so let me just do the computations. So what would be the integral from a to b of the real part dx? Well, we have to integrate, just substitute by this formula here, and then we integrate, and then we can swap the integrals. We can commute the two integrals. We have an integral from a to b and from minus infinity to infinity. Then we switch them, and we can switch because everything inside will be absolutely integrable. You can just integrate. Oh, sorry, no. You can switch. That's true also, but you can switch for a better reason, because everything inside is positive. So you can always switch integrals when everything inside is positive. But this thing is positive. So then we switch, and then if we switch, we get this a arctangent of b minus t over y plus arctangent. So I always write arctangent just as a tangent, and t minus a over y, the mu t. And what we used here was the fact that d dt of the arctangent function is just 1 over 1 plus t squared. Okay, or equivalently that d dx, that the tangent of x equals 1 plus tangent squared of x. That's what we used. Okay, so we do have that. Then what I want to do now is to estimate. Okay, but I need one more thing. Let me rotate here. I need one more thing, which is what? Oh no, that's okay. So let me just write now what is mu of b minus mu of a minus minus this thing. And compute the moduli. Okay, so this is exactly just mu b minus mu of a minus this this integral here. So what I want to do, I want to do the following. I want to split that integral from minus infinity to infinity in 3 parts. One from a to b, then one from b to infinity, and then one from minus infinity to a. Okay, that's what I want to do. And then the one from a to b, I can move this bit here to the inside of the integral, because I know that this bit here, so maybe I could even erase this bit here, since I'm assuming that a and b are points of continuity. This bit here is just the integral from a to b of the mu of t. Okay, so then I will be able to move this part here to the inside of this integral once I split in 3 parts, and then I move it to the integral from a to b. Okay, so let me continue with this computation. So we get that this is less or equal than 3 things. The first thing would be the part from a to b. Since we have a pi divide, oh, we don't have this y here, sorry. This was always 1, sorry. And there is a computation to be made using this formula, and that's what you get. Okay. Okay, so now let me just write this. So now I will split this integral from a to b, and once so the part from a to b, I will put this inside, then I get just a tan b minus t over y minus a tan of t minus a over y d mu t. And I should put the moduli here because I'm moving the moduli to the inside, plus the second part, which would be 1 over pi integral from b to infinity. And then we have just the tangent part. So maybe I should like, yeah, let me even simplify it more. Let me abuse this notation here. As long as you understand what I'm writing, that means the integral from a to infinity plus the integral from minus infinity to a. D mu t. Okay. So we have that, but basically, so let me maybe draw here the graph of the a tangent. So what's the graph of the arctangent function? Well, it's just, so you have here minus pi over 2, you have here pi over 2, and then you have here 2 asymptotes, and you have here something in the middle. So this is the a tangent function. Okay. So you see that whenever I take the a tangent, like I'm doing here, and I add two values of the a tangent, I'll always get a number between minus pi and pi, correct? Because these things are between minus pi over 2 and pi over 2. So therefore, when I do pi minus something, this thing inside will be positive. So I could actually even just, it won't be important, but this is a side remark. You can now just do that, because that's positive. Okay. Now you see more or less what is going on, because when I take, so I always think I'm taking y to 0. So this thing is going to infinity because, well, since t is between a and b, this thing is positive, this thing is positive. So when I take y to 0, this thing is going to plus infinity, and this thing is going to plus infinity. Well, but if when a tan goes to plus infinity here, I'm converting to, oh, this is plus pi over 2. Plus pi over 2 minus pi over 2. When I do this, then I'm converting to pi over 2, but I have 2 of these. So I'm converting to pi, and there's a pi minus this inside. So this whole thing is converging to 0 when I take y to 0, just because of the property of the arctangent. But if I want to use some kind of a dominated convergence theorem, I can't because, well, although this is going to infinity, this guy here is very close, could be very close to b as well. This could be 0, for instance, when t is b. So this would be fixed, fixed equals 0. So that may be a problem. So what you have to do is you have to remove a part here and put b minus delta and put a plus delta, and then we can apply this argument that when y goes to 0, this whole thing goes to infinity, and we get this pi over 2. You have to do this extra bit. Okay, and in these integrals in the bottom, well, they're basically the same. Well, the treatment you would do for this integral from b to infinity would be more or less the same as you do in here. So then I will only show that one of these go to 0, and the other you could do easily. Okay, so let me call these three guys here. Let's say we have three integrals. So I1 plus I2 plus I3. So I1 would be this guy, I2 would be this guy, and I3 would be this guy. Okay, so then let me analyze each one. So let me analyze each one. So I1, so what is I1? So I1, we have an integral from A to B. So what I'm going to do is I'm going to integrate from A to A minus delta, and then let's have one over I here, plus an integral, let's say from A plus delta, plus A plus delta to B minus delta, plus the integral from B minus delta to B of whatever I have inside, which is pi minus, maybe I can use a better trick. D mu t. Yes, great. So what happens now? So probably what I should do is select this whole thing. Yes, I should move this to the bottom. Raise this, put this dot here, and say, well, for some epsilon positive, choose the alpha positive so that, well, these A and B are points of continuity, so I can definitely choose delta so that this and this is less than epsilon, okay? Because it's a point of continuity. Great. So what we have here, so I'm integrating well, I should specify, to be clear, I should specify in this notation here, I should specify what I'm doing with these intervals. It's always annoying when I'm writing in this notation. So what do you mean by coming from the left or from the right? I always should specify, is this a plus or minus? Is this like a plus or is this like a minus? Okay. Well, let me assume that I'm always dealing with points of continuity. So let me assume that A plus delta is also a point of continuity and also B minus delta and etc. I can always do that. Why? And I will mention in a moment. Because, well, the points of the discontinuities of this function here, the mu, they are countable. Okay? So therefore, I can always take any, I can always assume that this guy is a point of continuity. Okay? So let me stick with that. I will explain in a moment why. Well, for each, maybe I can even explain it. Well, if you have a discontinuity of an increasing function, it means that it has a jump, okay? So for every discontinuity, so maybe I can even like write. So suppose I have a discontinuity here. So it means that it has a jump. So for each discontinuity P, you have an associated interval. And this interval is unique because if you have another one, like here, and this is a point Q, then this discontinuity here is associated with another interval, which is disjoint from this one. So that means that for every discontinuity P, there is an interval. Okay? This set of intervals doesn't intersect, and don't have any intersections. They're disjoint. That means that for every discontinuity, you can associate a unique, let's say, rational number. So therefore, the discontinuity is countable. You just pick any rational number in that interval. So for every discontinuity, you have a unique rational number, and therefore they are countable. Okay. So I can assume that A plus delta is a point of continuity. In any case, whenever I'm, so this part here, so let me bound this thing. So this thing will be less or equal than what? Well, I already argued that this guy here, well, this is positive, so this here is a number, positive number between 0 and pi over 2, positive number between 0 and pi over 2. If you sum, is a positive number between 0 and pi. Okay, so this whole thing here is less or equal than pi. Okay, so I can just bound it by pi whenever I like it. And then in this interval here, if I do that, then I just have, let me even write, then I just have like 1 over pi integral from a to a plus delta pi the mu of t. That would be me just bounding this by pi in this integral. So they can cancel. And what is that? Well, this is just mu of a plus delta minus mu of a. Yeah, there is. Yes. So this is just that, but this is less or equal than mu a plus delta minus mu of a minus delta, which is less than epsilon by choice. So I know now that, let me erase this whole thing, that these two bits, this one and this one, will contribute with almost epsilon each one. So I have a 2 epsilon. Okay, and then I have the integral in the middle. And for this one, I can do the argument I just said. Because now each one of these guys, this one and this guy, are both greater or equal than delta over y. Okay, so when I look at the graph, when I send y to 0, I would definitely be, if y is sufficiently large, sufficiently small, sorry, I would definitely be like from some point m on in this direction when I evaluate this thing. So therefore, when y is big, I would definitely be close to pi over 2. Each one of these two would be close to pi over 2. So therefore, be pretty close to pi. You can even do further, well, we can even use the following. We can use this thing here. We can use that a10, let's say, of s is pi over 2 plus O of 1 over s for s if s is going to infinity. Okay, something we can easily compute. So if you do that, what you get in the end, this is just 2 epsilon plus O of y. Okay. So if you use that thing here, that's what you show. So great. So when y goes to 0, this first integral will be at most 2 epsilon. Any questions in this computation? Great. So let's move to this, let's say, the second integral. And for that, I will use a certain identity. So you realize that, for instance, in the second integral, which would be this guy here, so t is always greater or equal than b. So this thing here is negative, and this thing here is positive. So they have opposite signs. Okay, so that would be good. Choose a certain identity, and the identity I'm going to use is this one. A10 of x plus A10 of y. This is actually A10 of x plus y divided by 1 minus xy. Okay. So that's the identity. And you can easily show that using trigonometric identities if you wish. Okay, so if I use that, what I get is the following. I get an integral from b to infinity, 1 over pi, and then I get moduli of a tan of y b minus a. Well, you have to do this identity with these guys here, so there is a computation to be made again, but then you get this plus t minus a, and then t minus b. This is the mu of t. Okay, but again, what I'm going to do is I'm going to separate this thing into parts, b plus delta to infinity. But the first one I will do just from b to b plus delta. Okay. Okay. And again, well, the very same argumentation. So the integral from b to b plus delta, you can just unfold this identity, you go back to this bit here, and do the same argument I did before. You're gonna get also a contribution of epsilon. So you actually can just do that. This is less or equal than epsilon plus 1 over pi, the integral from b plus delta to infinity of a tan this. Okay. And then what we do is, well, we use another easy to show inequality. Maybe we put it in here. Which is that, let's say, that a10, well, its derivative is 1 over t squared. So this is definitely this. Okay. Yes, and therefore this is, well, you just bound this t squared, you remove it. So this would be just the integral from 0 to x. So this is just bounded by x. Okay, very simple. It means that the derivative at the origin is like x. But then you have this bound. So if I just apply this bound here, okay, so you can just replace this by this. Okay, great. So then now this, so now this y I can put outside b minus a 1, okay, and then I can just remove this y here now. It's an upper bound, great. And I don't have any problems in the integral because I'm far away from b, and b is greater than a, so this is a converging integral. Okay, so writing everything nicely, this would be just 1 over t minus a, and then t minus b, the mu of t. Okay, that's what we have. Which is again just O of y. Because, well, the point is just to remove all the dependency in this integral of y. If I just remove the dependency of y inside the integral, which I just did by the most simple inequalities as possible, this one, and then I just remove this y here. Then I get this, and now this bit here converges and doesn't depend on y, it's just an O of y. So great, I just have a bound for the second integral, and the third integral we bound in the same way. So let me write here, same way. I2, the second integral. So then that finishes the proof basically, because then the conclusion is that the three integrals, which I wanted to show that converge to 0, would be less or equal than 4 epsilon plus some O of y. So then when y goes to 0, so these three guys depend on y, but it's always the same trick, the same technique. You just take the limit sup on the left-hand side in y when y goes to 0. And then that will show, this inequality will show that this limit sup is less or equal than 4 epsilon, but epsilon is arbitrary. Then you send epsilon to 0. So then you show that the limit sup of this thing is indeed 0. Therefore, the limit exists and the limit is 0. And that is showing what we want. So that would finish the proof. Okay. Any questions in the proof? Okay, so this wasn't the hardest proof in this class. The hardest one will be the one now. So we just show that we start with a measure and then we can extend it, this measure to an analytic function in the upper half plane whose real part is non-negative and whose real part, when you go back to the real line, kind of coincide with this given measure in the way, in this way here. Yeah, in this way here. So then you can ask the converse question. Suppose I start with a function which is analytic and has no negative real part in the upper half plane. Will that function be given by some construction like this? And the answer is yes. That's theorem 4. That's Poisson representation, or the converse, let's say converse of theorem 3, which is let f from C plus to C be analytic, real part of f greater or equal than 0 if y is positive. Then there exists some C and P real numbers with P greater or equal than 0 and non-decreasing mu of x such that, well, so f of z would be equal to 1 plus tz divided by t minus z, the mu of t, 1 plus t squared. So that would be exactly the formula we had before. But if you think about, it shouldn't be only that, because, well, the function minus I times z does have no negative real part in the upper half plane. And it's linear and will never be given by a formula like this. It's something you can realize. So therefore, we need to correct for linear factors, but that's all there is. So this would be C minus PZ. and that's it. Okay, so this part is just a linear factor correction, but other than this, it's indeed given by exactly the Poisson construction we did in theorem 3. Okay. So to show this, I will need to use something which is called Helly's selection principle. So let me talk about that first, and then we start the proof. This is a side comment. What a cool name this is. Helly's selection principle. Looks like an awesome theorem or something very nice with a very hard proof and so on. I wish if I can manage to prove a theorem that has a cool name like this and remains throughout history, like and people use it a lot, let's say, I would be very happy mathematician. But actually, it's very simple, and the proof is very simple. It's something useful to know. So what is that? Suppose you have a certain sequence, let's say, of non-decreasing functions. Okay. And again, if you Google this thing, you see that a bunch of generalizations to Banach spaces, etc. I mean, I don't know, to well-ordered sets, I don't know, things like that. But this is the simplest version of it. So suppose you have a sequence of the decreasing functions on an interval, let's say AB. And so let's assume, that mu n of A and mu n of B are bounded sequences. Okay. Then there will be some subsequence nk and some non-decreasing function AB such that mu nk converges to mu for all x in the interval. Not almost everywhere, but for all x. Okay. That's the Helly selection principle. And the proof is actually quite simple. Let me prove it here. So why we need that first? Well, we will prove theorem 4 by using some kind of approximation argument, and we'll have to take a limit of some non-decreasing functions, and then Helly selection principle will help us with that. Okay, so proof. So the proof is like a kind of what you can do. I mean, you have no idea what to do when you have something like this. And you just do the most obvious thing, which is, well, if I just pick a point and, well, I know that the sequence mu of x is bounded. For any x in B. Well, just because it is trapped between 2 points. And I know that these two guys here are bounded, okay? Indeed, it's like uniformly bounded for every x in the interval. So therefore, for any x, I can take a subsequence that converges, okay? So if I pick a second x, and I can do the same thing. So if I pick a third x, I can do the same thing. And then by doing a Cantor's diagonal argument, if you take a countable number of points, you could take a subsequence that converges in each one of these points. So then I would just take the rational numbers. So by Cantor's, so let's say using Cantor's diagonal, let's say procedure, there exists a subsequence nk such that mu nk of x converges to some function mu of x for every x rational in the interval, and mu of x in principle is only defined on the rational. It's just the value you get in the limit. Okay. Great. So what you can do is that you can extend this measure mu. Keep saying measure. This function mu to all the other points in the interval AB as you like. You could just extend it as you like. So I will extend it in a way. So then extend mu by, let me just use it so it's normalized. So I would say limit when y goes up to x and y is rational of mu of y plus when it goes down. So just do the average of the lateral limits. Okay, that's one. You could do anyway. Okay, as long as you take a number which is between these lateral limits, you should be fine. Okay, so then you realize that mu now is defining the whole interval, is not decreasing. Okay. And then I would leave as an exercise to show, it's a very simple exercise to show, then it's easy to see. See that actually mu nk of x converges to mu of x if x is a point of continuity. Is a point of continuity of mu. Okay. So therefore, the sequence you created, the subsequence you selected, actually converges to mu in all these continuity points. Okay. Well, the remaining points on the AB, they are actually they are countable. Okay. So the discontinuities how do these continuities like this? Anyway, maybe that's not the right English. Discontinuities, let's say, of mu on AB. So say the set is like S is countable. Okay. So what you can do is, well, basically you just go ahead and just redefine mu in this countable set by doing what? Well, this sequence mu nk will definitely be bounded for each point here. Okay. So then you can do again a Cantor's diagonal argument and subtract a subsequence of the nks that will converge to something in this set S. Okay, and then you define this something as mu. So redefine mu on the set S as this limit. Okay, Now, the subsequence you took in of NK will still be converging to mu at the continuity points of mu. Okay, but then on this set is now converging as well, and then now it will converge for every point, and you won't be changing. And then you have to show that by doing that, you won't be changing the continuity set of mu, and etc. Okay, so I will leave you to finish the result here, because I don't want to get, it's an easy exercise. So then further take a subsequence, let's say nkj, and redefine mu on S by mu of x equals the limit of mu nkj of x, and show this solves, and show that everything is still consistent. That means that, so now we converge on S, it will converge on the other points as well. So now show this is the mu we want. Okay. Basically it's done here already, because it's still converging to mu on the continuity set, is now converging on the set S as well, so it's converging everywhere. Maybe the continuity set of mu will change anyway, but it's converging everywhere. And mu is still non-decreasing when you do this change. That's just, again, a simple computation you can do. So still mu is non-decreasing. Okay, so it's a basically very simple kind of proof. Just do what you can do, and that solves it. Any questions here? Okay, so let me go to the proof of theorem 4. So let me just revisit. So what we want to show is that, well, I give you an analytic function, no negative real part in the upper half plane. Yes, no negative real part in the upper half plane. And then I want to show that this function can be represented this way. Okay, so that's what I want to show. So let me continue. So proof. Maybe I should make this remark here as well. So what you can show is that if once you have built this limit mu, then you can show that the integral, let's say, of g x, if g is some continuous function, let's say would compactly supported in the interval AB, something like that. I think just continuous in the interval AB should be fine. So maybe I should say integral AB the mu n of x. If I do this, then this will converge. Well, once I've taken the subsequence that converges actually to mu, this will be converging to the integral of A of B, the g of x, the mu x. Okay. So that's easy to show because, well, first you assume that mu g, so this should work for every g continuous. Let's say g, we put here on top, g continuous. So why this should work for every g continuous? Well, assume first that g is C1, and then this integral here you can do by integration by parts. And then once you do it, then you use, then you just have a sequence of functions converging pointwise to another. Then you use the dominated conversion theorem to prove that So if it's C1 is okay. And if it's not C1, you just take a continuous function and you put a continuous function that is greater or equal than this, sorry, if it's not C1, if G is not C1, then if G is continuous only, then you just bound it by a G1 here and a G2, 0, and a G0, G1, C1. Okay, then you just do this trick, and then you get the result for continuous. Okay, bottom line, the integral of a continuous function converges to the integral of the limit. Okay. Okay, so now let's go back to the proof of theorem 4, which is here. So now we will do problems, we will use problems 2 and 3. So problems 2 and 3, what they say, let me just do a quick review of the problems. They say that theorem 4, as it is actually true. That's what they say. If we assume further that the real part of f, so this theorem here is actually true, if we assume that the real part of f is continuous on the real line, it extends up to the real line as a continuous function, okay, which I'm not assuming in here, okay. So theorem 4 follows from the problems if f is continuous, okay. So they say that, so they say if real part of f of x is continuous, then theorem 4 is true, and then the mu of x would just be real part of f of x dx. Okay, that's what the results of theorem 2 and 3 shows us. And if you use problem 4, so in particular they show that once you take the real part, let's say x plus iy, this is some py plus y over pi, real part of f of t, t minus x plus y squared dt. Okay, where p can be computed as a limit when y goes to infinity of the real part of f of iy divided by y. And this is problem 4, actually. Okay. Great. So we will use that. Now, I don't have the assumption that real part of f is continuous on the real line. So I have to do something else. So what we do is this simple trick. We add some epsilon to the function. So when I do this, when I put on the real line, x, when z is real, I still am in the upper half plane because this would be just x plus I epsilon. So therefore I can use this formula because I'm not on the real line yet. So then there will be a p epsilon here, a y plus y over pi, integral from minus infinity to infinity, of the real part of f of I epsilon plus t divided by t minus x. Oh, this is a square here. Squared dt. Okay. So this is for every y positive. But by problem 4, I do know how to compute this p epsilon, would be this limit, but with this guy replaced by iy plus I epsilon. But then if you realize, well, it will be the same limit because I could just add epsilon here and then multiply and divide by y plus epsilon, the limit will be exactly the same. So this p here actually does not depend on epsilon because of problem 4. So this is just some number p. Great. And this guy here, I will define this new measure here. So so this would be of, say, d mu epsilon of t divided by t minus epsilon squared plus y squared, where mu epsilon, where epsilon t is just the real part of f of I epsilon plus t dt. Put it here. Okay. Okay. And then now I will use Haley's selection principle, because now I have a sequence of measures, mu. So so mu epsilon would be just a primitive of this guy. If you want, I can even write it here. Mu epsilon of x, let's see, yes, it would be, I have to write it, mu minus, let's say, b minus mu epsilon of a is just the integral dt from a to b of this guy here. Okay. So this defines, this thing defines uniquely modulo adding a constant, which won't make any difference, non-decreasing function mu epsilon, which would be just a primitive, any primitive of this guy, which would be positive because this guy is positive on the upper half plane. Okay, so I have a sequence and I want to take a limit. So by Haley's selection principle, because I want to take epsilon to 0, so by Haley's selection principle, there is a subsequence which I always denote by epsilon. So I always think that that I'm taking under a certain subsequence that mu epsilon of t converges to some mu of t when epsilon goes to 0. But I always keep in mind that under a certain subsequence of epsilons going to 0. Okay. So now I have my candidate for measure. This guy here is supposed to be the measure of the theorem. Okay, so how can we prove that? So first of all, we do have that, what we do have? We do have the following. We do have that, let's say, mu epsilon of a minus mu epsilon of minus a equals the integral of minus a to a of the mu epsilon of t. And then we can just bound this by 1 plus a squared, integral from minus a to b, the mu epsilon of t divided by 1 plus t squared. So basically I just multiply it and divide by 1 plus a squared, but inside the integral I can bound it by just by 1 plus t squared. Okay, great. But then you realize that, oh, sorry. Oh, yes. First of all, I need to show why I can apply Haley's uncertainty selection principle. And the reason why is that in here, I'm just explaining that these numbers here are bounded by this thing, okay? And we do know that this is bounded because this thing here, because integral from minus infinity to infinity of d mu epsilon t over 1 plus t squared, this is just, if you take a look, is just real part of f of I y plus I. So x is 0 and y is 1. Oh, there is a p here. So p plus this equals to that. I just go here in this formula and put I equals z equals I, and then you get this. So in particular, this is true. Okay, so this integral is uniformly bounded, because when epsilon goes to 0, this is just a real part of f of I, which is a number. So this thing is uniformly bounded, and then I can apply Helly's selection principle, because this thing will be uniformly bounded for every A, which means that each one of these guys is uniformly bounded. So then I can apply Helly's selection principle. Okay. Well, what I'm saying is, well, Helly's selection principle, you can always, so there's still a minor problem here, which is that, well, I know that this difference is uniformly bounded. Okay, how do I know that each one is? Well, mu epsilon defines the same measure modulo adding a constant. So for instance, I could just add this constant here and redefine mu epsilon. Okay. In particular, it would be, let's say 0 at the point minus a, I don't care. In the end, upon redefining mu by adding some constant to it, then I could apply Helly's selection principle. Okay. Is this that part looks clear? Okay, great. So anyway, I can apply Helly's selection principle, and then I have a limit, and then I want to show that this limit is the one that I want. And this is more or less simple to show. Okay, so so what do we have? We have the real part of f of z plus I epsilon. This is what? This is definitely great then by the identity we had before. If I just truncate the integral from some point minus a to a, this is definitely true. Just went to this identity here and truncate this integral. Okay, so the integral is truncated. So this is true. So then when I take epsilon to 0, I will conclude that, so then I will conclude that real part of f of z is greater or equal than p of y. Again, because of that comment that I said that if the function is continuous, then the integrals against the function converge to the limit. So this would be just that. But this holds for every a, then I take a, so this is epsilon to 0. Then I take a to infinity, and then I can just, and I have this. Okay. So again, so we always had this bound. Then I just take epsilon to 0. And then after I take a to infinity, and you conclude this. In particular, we get that this thing is finite. Okay. Great. So now we can define a function. So now define, let's say, h of z equals minus IPZ plus integral from minus infinity to infinity 1 over pi I over 1 plus where is it? Yes, 1 plus, yes, 1 plus t. I always confuse it, 1 plus or 1 minus. One plus t squared. Okay, so define this guy so that the real part of h is exactly this guy. So we want to show that real part of f is equal to real part of this guy, of h. But right now we don't know yet. Okay. So then we conclude that the real part of f minus h. Oh, this is not h, this is supposed to be g. So changing your notes, this is supposed to be g. So I follow my notes here carefully. So this guy is greater or equal than 0, but just because of this inequality here, we just showed. So we have that. Okay, but what else? Well, if I integrate from a to b, say now say h is f minus g. So if I integrate from a to b, the real part of h of x plus I epsilon dx, okay, what is that? That is the integral from a to b of the real part of f of x plus I epsilon dx minus the integral from a to b of the real part of g of x plus I epsilon dx. So what is this conversion to when I take epsilon to 0? Well, by definition, by construction, this is mu b minus mu a for every point ab, because well, we were taking the limits of this measure. Oh, these have to be points of continuity, otherwise this won't be the case. This should be the integral from a to b. So maybe I should say, and a and b points of continuity of mu. So this is by construction, because these measures are converging to, these measures here are converging to the measure mu, or these functions are converging to this, if you want. And now you have this guy g, but this g is defined by this formula, and then again by appealing to the theorem we just proved, okay, which is theorem 3, is a Poisson representation defined by this measure, and we showed that when you take this limit here, this indeed converges, if it's a point of continuity, to mu b minus mu a. Okay, so this is by construction. By construction is this part, and by theorem 3 is this part. Okay, so this is 0. Okay. Great. So, and moreover, we also have that since we have the same P here, P for G, and the same P for F here, okay, and this limit, this P can be computed this way, the same as for G, we do know that the limit when y goes to infinity of h, the real part of h of iy divided by y is 0. Okay, so putting all those pieces together, we get by using problems 2, 3, and 4 that the real part of z plus I delta, let's say, where delta is some number delta positive that will fix, to not be confused with epsilon. This is just this. Well, I could just take the difference of the formulas, but I don't want to do that in the moment. I want to do that in a slightly, above a vertical line, which is slightly above the real axis, okay? So then I can put h here. Okay. That's what we have. So this is positive, well, you know, the real part of this guy is positive, but we can just bound this thing by what? You can just the most naive possible bound and just delete this guy. Is that what I want? Yes, I just delete this guy and I have just 1 over pi y integral. Oh, no. Yeah, I want to do that in an interval. So we have the 0 is less or equal, let's say, than y over pi integral from minus a to a real part. So recall, all we want to show now is that this function h has 0 real part. So, and that's why it requires some work. So that, because we want to show that basically f equals this function g I define, which is almost like the f from the theorem, but a constant, because the f from the theorem, let's go back, yeah. This is the f from the theorem, which is exactly like g, but from this constant here. So we want to show that this function h has 0 real part in the upper half plane, and therefore it should be just a complex constant, and then that would finish. So that requires some work, and that's what we're doing here. So let's go back. We have this integral. It's positive because, well, h is positive. And then I do that naive bound that I just said. Okay. I just throw this away. But then, what do I know? Well, I do know that when I take delta to 0, okay, this is 0. At least for some sequences of delta, which would be exactly those for this epsilon. So maybe I should put this delta equals to that epsilon. So let me maybe write it here. So if I take delta equals epsilon, those sequences, those epsilon converging to 0, for which this calculation here was possible. So this converging to 0, then I know that this bit here converges to 0. So let's say if delta equals epsilon is going to 0. Okay. So now I know that, great. So now I can use this information back in the formula for h. That is definitely the limit when, let's say, then I will now put epsilon, delta equals epsilon. Epsilon going to 0 of this thing. Oh, sorry, of, let's say, real part of h of z plus I epsilon, which we do have a formula, which is this. Okay, but if I split this formula between, let's say, minus a to a, and again, I had to make an assumption, maybe you missed. I used this thing here, which only works if A and B are points of continuity. So I'm assuming that A and minus A are points of continuity of mu, which I can assume because, again, the points of there's continuities at most countable. So I can always take A, such that these are points of A and minus A. Oh, sorry. A and minus A are points of continuity, and A can be as large as I want. Okay, so going back to the argument, I do have this, then, well, this is the limit when epsilon goes to 0 of this integral. But for any point of continuity, from minus A to A, that limit converges to 0. So this I can actually make it as an integral from A to infinity plus an integral from minus infinity to A of whatever I have here, y over pi real part of t plus I epsilon divided by t minus x y squared dt. Okay, and then we are almost finished. Yeah, it's like 2 minutes over the normal time, but anyway. So now we do have this, great, and this works for any A, let's say large, and let's say positive and large, and a point of continuity. Okay. So then now what you can do is this very simple trick, which is if, let's say minus A, let's say x1 and x2, and let's say t is a value outside, which is exactly the stuff inside this integral, then we can do that it's a simple inequality to prove this is less or equal than 1 plus x2 minus x1 in moduli divided by the minimum of A minus x2 and then A plus, let's say x2, and everything is squared. So basically it's the distance, this is, this stuff here is the distance of x2 to the boundary of the interval minus AA, and you have this thing here. So you removed completely the dependency on y and t. Okay, this is easy to show inequality. So if you use that inequality here, together with this limit, that would imply that the real part of h of x plus x1 plus iy is actually less or equal than this, x1. Oh no, this is supposed to be x2 then. x2, and then you have this. Squared, and then this would be again real part of h of x1 plus iy. Okay, and this works for any a large point of continuity, so I can take then a to infinity, and we just conclude that real part of h of x plus x2 plus iy is just less or equal than the real part of h of x1 plus iy. And all this, and this less inequality was possible just because I could remove any, oh, this is wrong. This is minus a. I could remove any big interval from this integral. Okay, so since I can do that, then I can apply a simple inequality to make this trick here work. And once I have this trick, I send a to infinity, then I have that. So that implies that real part of h of x plus iy, because I can just flip x2 with x1. I put no conditions of x1, x2. So then I will have that h of x2 iy is less or equal than x1 iy is less or equal than real part of h of x2 iy. So therefore, that this function is constant along horizontal lines. So it's just some c of y, okay? And now it's easy to show, and I will leave you to finish, that if that is true, then it's not hard to show that, but in particular, if you differentiate h in z, then you would get that the real part of the derivative of h is 0. So therefore, the derivative of h should be a complex constant. Okay, so then you can go back, and then so h will have to be linear with the constant multiplying the variable z to be purely complex. But then you have to show that this constant have to be 0, because we do have, recall that we do have this thing here, and this thing will remove any linear term from h, and then you show that h is just, so then it's not hard to show that h is just constant equal to some complex constant, and c real. Okay, so then that will show that f equals g plus some ic, and that's exactly what we wanted to show. So that would finish the proof. Okay, so it's a tricky proof. Mostly in the final part, after to take it to the limit, you have to use some kind of little tricks. It's a bit involving because you use a trick in several places, but anyway, it's not that hard to understand. It's just a bit tricky, but you have to put some work to show that that mu that the Helly selection principle gives you is exactly the mu you wanted. Okay. Any questions in this proof? I can go all over again if you just quickly if you want. Great. So that finishes the class for today, and I hope you enjoyed. So now we know how to what a function on the upper half plane with no negative real part is. It has to be something given by the Poisson representation, and we will use that in the next classes. And we don't have any problems for today, besides the ones I already gave you. And I will stop recording now. Thank you. No, stop.